I'm speaking about Numba Enzyme, which is basically the work towards having enzyme be able to differentiate most of Numba, mostly on the CPU side right now. So for everyone, I'll first speak about what actually is Numba for someone who hasn't seen it before. What does a compilation process for something like typical Python code look like with Numba and the different stages? Where does Enzyme integrate? What are the next steps? And I'll give a quick summary and open the floor for questions. So what is Numba? Numba at its core is essentially an LVM JIT compiler, which was initially conceived for taking Python code in and then building this heavily optimized code and running it. This has been advanced and expanded to do both for CPU and for GPU, and is heavily optimized for NumPy computation primitives as well as Stanzel computations. And it is able to utilize a lot of differentializations in there. So it has its own vectorization engine, which basically uses a work queue. It has OpenMP, frame building blocks, and the one that's actually used most often these days, CUDA. And that basically is the base building block which powers quite a few ecosystems, like the Rapids.ai ecosystem that some people have probably used, where the CUDA.gl compiler compiles all the different data graphs and speeds everything up on NVIDIA GPUs. Azara is one example, awkward arrays. Yeah. The key point here that people like awkward, for example, exploit is a Numba JIT has very different performance characteristics to something that's, let's say, the JAX JIT. And that is, for example, if you have a very long computation where the JAX JIT suddenly begins to increase its compilation time exponentially. Numba doesn't have an issue, and especially also with Stanzel computations and loops, that's something where Numba really shines. And that's why people also in computational physics heavily like Numba there. Typical setup is you have sort of this NumPy API in the front end. You get a graph out that you can rewrite if you want. For example, Azara does a heavy symbolic graph rewrite there. Then, for example, CUDA has its own optimization passes to optimize for something like an A100, H100, and so on. And then they go into the rest of the Numba ecosystem. This is now to go through a stage of Numba compilation. So if you compile a Python code with Numba, what does it actually do? So Numba internally matches the Python function to the bytecode. Then that's something where it applies the bytecode analysis to, where you have an untyped IR. On that, it performs its own type inference. You have a typed Numba IR. And then it lowers it into LVM IR and then applies the JIT. So just picking out these 4 key points here right now, which are the ones that we are most interested in. So let's just look at that. So basically, we have a Python function which goes into this untyped Numba IR, does type inference, you have the typed Numba IR, LVM IR, and then we have the LVM JIT. So first, we basically do a bytecode matching here. Then we get the untyped Numba IR, which Enzyme doesn't really want to work on. And then what we're actually more interested in is the typed Numba IR. And then this goes into LVM IR, on which the JIT is performed. So what does Numba Enzyme actually do right now? So right now, what it does, it applies itself to the typed IR to insert the shadow. And then we create the enzyme call on there. And then we call Enzyme as a compiler plugin on the LVM JIT. So first, one of the issues was that LVM Lite had a restriction in there that basically didn't allow plug-in loading. That has been basically mitigated now in collaboration with some of the Numba maintainers. And that's already available, so that is like fully resolved. And so the next steps now are making it more stable and distributing this is right now a reverse mode prototype to just have to distribute the reverse mode prototype and push it up. And then to heavily more seed the type inference of Enzyme itself with Numba's type inference and deeper utilization of Numba's real infrastructure. That's those are the main next steps, and also more primitives such as forward mode to allow sensitivity analysis, vector modes, Jacobians, and Hessians. So this is all inside of this enzyme JIT'd decorator, which is only reverse mode right now. We're not exploiting numbers type inference yet. That's the main next step. And yeah, I'm open for questions.
Okay, thank you, Ludger. Any questions? Any comments? I'm going to ask about opinions on Python, I guess. Okay, I think everybody just wants their coffee because our next stop is a coffee break. But I've got a question from Valentin. Nice.
Yes. So you mentioned that you insert the enzyme autodiff call during into the typed IR before you then do the LVM code generation. Why that interface?
Because the rewriting infrastructure of Numba makes it a lot easier to do it on the typed Numba IR instead of the LVM light interface, which is a lot more restrictive.
But so the question is, like, Enzyme operates on passing shadow for the arguments in and out.
Yes.
Right? And so normally the user is responsible, like in C++ Enzyme and in Julia Enzyme, to allocate the shadow of their variable because they might know best what that's supposed to look like.
Yes, but so the way this is constructed right now is to basically make it as seamless that you basically can just replace the JIT and then but the issue there is basically that we are essentially mirroring the forward data structure more directly. So this introduces, as you probably know from Enzyme.jl, it introduces a bit of, or a bit is good, like introduces overhead because you're basically doubling the data structure.
Right.
So so to make it much tighter and have less memory overhead, one would need to do what you're describing, yes.
Okay, let's thank Ludger again.
I think that's